feel the vibe.
What's up, guys? Welcome back to another Algebra 2 instructional lesson here with Mr. Gaines as we continue our exploration of radical expressions and radical functions. We're actually going to bring into you a new concept for most of you that can be related back to what we talked about in the last target when we were dealing with radical expressions, simplifying them, and working with their operations. Radical expressions are actually just another form of exponents. So we can connect radicals to rational or fraction type exponents with this rule right here. So if we're given A, that's going to be a real number, and B and C that are integers, we're going to have this base, this is what we call base, A, to the power of B over C, the fraction B over C. We can rewrite this as a radical expression. So the rewritten form of this radical expression would be A to the B power, the base, to the power of the numerator in our fraction, to the C root. So the numerator of the fraction becomes the power of the radicand, the exponent of the radicand. And the denominator of the fraction becomes the power or the index of our root. Now, the order in which we do this does not necessarily matter, or it does matter. It's useful to be able to manipulate that order, but it can be switched around. So if I want to rewrite A to the B over C power, I can take the Cth root of A, where again the denominator in my exponent fraction becomes the index of my root, and simplify that first, and then take that to the B power. So anytime we have a base, a number, a real expression, or a real number, A, and we take it to a fraction power, the numerator becomes the exponent of the radicand, and the denominator becomes the index of the root. So we can connect this new idea in RF.2 rational exponents with the concept of radical equations that you guys are used to. Now let's see where that's going to come into play. In order to use these concepts, it's going to be focused primarily on exponents. So let's quickly review our exponent rules. So for any x or y that are not equal to 0 and a and b that are real numbers, if I have two terms that have the same base, x and x, and I am multiplying those two terms, I can add their exponents. That is the product property. The quotient property tells us that, again, if I have the two bases that are the same and I divide those two terms from one another, I can subtract their exponents. The power property, if I have a base to a power, x to the 8th power, and I'm taking that expression to the b power, I can take the exponents and multiply those together. The zero power property tells us that any term to the 0 power is always going to be 1. And when we're dealing with negative exponents, a negative in the exponent is a reciprocal operation. So an x to the negative a power is the same as 1 over x to the a power. Also, x over y to the negative a power is the same as y over x to the a power. So all of these properties you guys learned and used in Algebra 1. And we're going to continue to use them here in Algebra 2 when we're starting to deal with rational exponents. So if you do need to, pause the video and write those down, because I'm going to refer back to them as we progress. Now let's take a look at examples. There's really only one type of example that right now we're going to focus on in rational exponents. Eventually we're going to do some solving of equations, but right now we're just going to work on simplifying rational exponents. So for problem 1, it says simplify each of the following by rewriting the expression in lowest. Let's change that from radical to rational exponent form. So basically we want to simplify, and in this we're going to assume that all variables are positive. So if we go back to our radical rules that we talked about, when you simplify an even root or an even indexed root, you need a positive response. We're not going to worry about that too much right now. We're just going to assume all variables that we encounter are positive. So let's go ahead and take a look at some of our examples. So in problem 1a, If I were to think about rewriting this into something more familiar with a root, I would rewrite this as 4 being my radicand. The numerator 1 would be my power, and the denominator 2 of the fraction would be the index of my root. So essentially what this is asking for is a simplified version of the square root of 4, which is 2. So with numbers, you can definitely do this in the calculator. So if I go to my calculator and I type in 4, and I get to that exponent and type in 1/2 power, I'm going to see that the answer is 2. But we are going to need to be able to connect these ideas with variables that our calculator won't do for us. So we're going to make sure we walk through these terms algebraically and show our work on this process. Let's take a look at B. B is 16 to the negative 1/3 power. Now again, you don't necessarily have to rewrite this, but if we did, the negative takes the reciprocal. So I could rewrite this as 1/16 to the 1/3 power. The 1/3 power would be the same as the cubed root of 16 to the first power. Again, the denominator becomes the index of my root, or the power of my root, and the 1 becomes the exponent for my radicand. Now, if I remember my perfect cubes, this is great. If you don't, again, we can go to the calculator and type in y equals x cubed, go look at the table, and we see that 16 is not a perfect cube, but it can be simplified. So if we were to simplify this, we would break this down into 8 times 2. So the 1 over the cubed root of 8 times 2, which is equal to 1 over 2 times the cubed root of 2. And we could rationalize the denominator here. I'm not going to focus on that right now. If we need to rationalize the denominator later, we will. But let's go ahead and let's turn this back into a rational exponent. So we would have 1 over 2 times 2 to the 1/3 power. So the cubed root of 8 is 2. And then we have 2 that's in a cubed root, which would be 2 to the 1/3. Now if I want to simplify this here, using our exponent rules, remember I have 2 bases that are the same, so this is basically 2 to the first power times 2 to the 1/3 power. So I can write this as 2 times 1 plus 1/3, or 1 over 2 to the 4/3 power. So depending on how the exponent, or what the answer is looking for, we could have an expression equivalent here, where I wrote it in its most simplified terms using rational exponents. We could potentially have an answer here as well, where you did not combine the 2 bases, even though we could. But this is how we can use exponents to rewrite this function. Now let's take a look at C. C is going to come up with a little bit better of an answer. Notice now that we do have a numerator other than 1. In both cases before, we had the 1 as a numerator, which would take the exponent of our radicand to be 1. In this case, we have a 2. So let's rewrite this as, if you wanted to, again, if you need to put it into radical terms to visualize, this would be the cubed root of 27. And now that 2 can go either inside the root and be done first, or outside the root. I'm going to go ahead and leave it outside because we can see that 27 is a perfect cube. So the cubed root of 27 can be simplified to 3, and then that 3 would be squared, which our final answer here would be 9. Again, I could check that in the calculator. So if I did 27 to the 2/3 power, I would get the response 9. So if you need to, you can break that down into a radical so you can visualize that process, and then put that back into a whole number using the exponents. Let's take a look at D. D would be -8 as my radicand. Then it would be the cubed root of -8, because that is the denominator of my rational exponent. The numerator would be the exponent of the radicand, either done before or after the cubed root. I'm going to write this as the cubed root of negative 8 to the 4th power because the cubed root of negative 8 would just be negative 2. And then I can take negative 2 to the 4th power. So if you need to, we can jump over here to the calculator. You wouldn't necessarily need to type in the negative because you know that anything to an even power is always going to be positive, and we'd come up with 16. So here we can see kind of the written out process for simplifying real numbers using rational exponents. Now let's take this a little bit further and start to look at, actually, sorry, I got one more example here with a rational exponent, a real number. Let's see if you can pause the video at this point and complete part E. So hopefully you got a chance to do E. E's a little bit tougher here. What we see here with E is if I want to write this in the square root term, notice that there's a negative at the 3/2. So what that does is that's the reciprocal operation. That means we're going to take this negative 49 and put it in the denominator of a fraction. And then it's going to be to the positive 3/2 power. So now I would have 1 over, if I want to write this as a root, this would be the square root of negative 49. Because the 2, the denominator, would be the index of my root, to the 3rd power, the numerator of the rational expression. The square root of 49, we should know, is 7i. So remember, if you take the square root of a negative number, you're going to have an imaginary answer. So my answer here is going to be 1 over 7i cubed. And we can go ahead and simplify this. 7 cubed would be 343, and then I cubed is I cubed, but we can reduce I cubed into negative, so this would be negative 1 over 343 I. Now if you wanted to write this in the standard form for imaginary numbers, we could multiply by I over I, which would give me negative I over 343 I squared. And I squared would be negative 1, changing this into 1 over positive 1 over 343, and then I. So either of these would be okay if we wanted to put it in the standard form for imaginary numbers. We would write it down here on the bottom. If it didn't tell you to, up here on the top is okay. So don't forget imaginary numbers when we start to simplify rational expressions. Now with variables, the same rules and properties maintain. So if I take a look at F here, I see that I have n to the 4th time, or to the 3/2 power. Now I could work on rewriting this if I wanted to. I could rewrite this as n to the 4th, and then take the square root of that, and then cube this. This would be an okay way to work through the problem. You'd get the same answer, but there's a shortcut. Remember our power property. So our power property tells us that if I'm taking a base with an exponent to an exponent, I can multiply together my exponents. So maybe a faster way for doing this problem here in 1F would be to take n to the 4 times 3/2 power. And if you take 4 times 3/2, that would be 12 over 2, which would be 6. So n to the 6th would be our answer there. So here we're basically seeing a way that we can get around putting this into a radical expression by using our properties of exponents that, again, you learned in Algebra 1 and we reviewed earlier. Now let's take a look at G. In G, I have both both real numbers and variables. So in this case, I'm going to take my power and essentially distribute it. So I can rewrite this as 216 to the 1/3 power times R to the 9 times 1/3 power. Again, I have a power, R to the 9th, and I'm taking that to a power, 1/3, so I'm going to multiply those together. Now, 216 to the 1/3 would be the same as the cubed root of 216. If I take a look at my calculator, the cubed root of 216 does work out. It simplifies to 6. So if I needed to, I could rewrite this as the cubed root of 216 because I have a 1 in the numerator, so it would be 216 to the 1st power, but the cubed root of 216 is just 6, so I'm going to write this as 6. Then I'm going to have r to the 9 times 1/3. 9 times 1/3 is just 3. So this simplifies to 6r to the third. So again, if we can rewrite and put these into roots and then simplify from there. But if you remember your exponent properties, it's going to help you go a little bit faster through these problems. Let's take a look at h. So in h, I notice that again, I have a negative here. So I'm going to first do the reciprocal operation. So I'm going to change this now into 9 over 4x to the 6th times, 4x to the 6th to the 5/2 power. So this again comes back from one of the properties that we wrote down here at the beginning, the negative exponents, that the reciprocal function would flip the fraction and take the exponent from negative to positive. Now from here, if I could simplify inside the parentheses, I might go about that route. In this case, I cannot simplify inside of the parentheses. So what I'm going to do is essentially distribute, if you will, distribute the 5/2 to everything. So 9 to the 5/2 over 4 to the 5/2 times x to the 6 times 5/2 power. So x already has an exponent there. I'm going to multiply it to the 5/2 power. So if I wanted to rewrite this again, I could rewrite this as the square root of 9 to the 5th in the numerator. In the denominator, the square root of 4 to the 5th. X to the 6 times 5 over 2. So 6 times 5 is 30 over 2 would be x to the 15th. And you can use your calculator for that. The square root of 9 would be 3, and if I take 3 to the 5th power, I can rewrite that as 243. The square root of 4 would be 2, and 2 to the 5th power would be 32. So my final answer for this one would be 243 over 32x to the 15th power. So here again, we're working through those properties one at a time, first using the reciprocal one and then the power property to be able to simplify our expressions. Let's take a look at I. In I might look at trying to reduce my roots because I have the 1/3 power, which is the same as a cubed root. Or I could start to use some of my radical equation concepts. So remember that we talked about multiplying roots. So if I have the square root of a and the square root of b, I can rewrite this as the square root of a times b. Well, essentially what we have here is the same concept. Remember the 1/3 powers shown are just cubed roots. So basically what I have is the cubed root of 3x times the cubed root of 72x squared. So what I can do here is multiply the two numbers that are inside my two bases, 3 times 72, which would be 216, and x times x, which would be x cubed. And then this would be taken to the 1/3 power. Now, the reason that I wanted to do that here was because I can essentially distribute my 1/3, take the cubed root of each of these. So 2/16 to the 1/3 power times x to the third times the 1/3. So x to the third times 1/3 would be that power rule again. And then 216, the cubed root of 216, we can see that again. I have those perfect cubes listed over here on my calculator. The cubed root of 216 would be 6. 3 times 1/3 would be 1. So my answer here would just be 6x. So because rational exponents are the same thing as radical expressions, we can use the same properties that we had with radical expressions with rational exponents. So go ahead and pause the video at this point and see if you can do J. Hopefully you got a chance to work through J. J is essentially the same type of problem. So here I notice I have roots that are the same. They're both 4th roots because the exponents are the same. So I can multiply together the basis, or what would eventually be the radicands if I rewrote that. So this would be 81 x to the 4th, y to the 4th, and all of this to the 1/4 power. So again, I could take this 1/4 and essentially distribute that. 81 to the 1/4 power, x to the 4 times 1/4 power, y to the 4 times 1/4 power. And now 81 to the 1/4, I don't have my 4th roots up here, my quartics, but if I go x to the fourth, I can see that 81 is 3 to the fourth power. So essentially, the fourth root of 81 would be 3. And then x to the 4 times 1/4 power would be x to the first power. The same thing would happen for y. So you should get just 3xy. So what's good to note here is we can use our exponent properties, but we can also use our properties that we learned with radical expressions, because anything that has the same exponent, the same rational exponent, is the same type of radical expression. So it works both ways here. Let's go ahead and let's eliminate k. I don't like the problem k. We could work through that one. You could work through it if you want to for fun, but we're not going to go over that problem. Let's take k off of here. And then what we'll do is we'll leave L, M, N, and O and P for practice in the future. So this is a good place to stop. When we reconvene in class, we'll have an opportunity to go over questions and then get a little practice in before we move into some more advanced problems. As always, thank you guys for tuning in, and I'll see you soon.